Good afternoon, lads and ladies. We are to a place now where, well, welcome to class. Today we are going to talk about the fundamental theorem of calculus and try to connect a little bit more of the things we've been doing with the concepts of last week and the rest of the time. Last time, you may remember, we talked about the definition of the definite integral. We spent a lot of time talking about notation and looking at some properties of the definite integral. So let me put it over here. Today is the 18th. And today we're going to do more on the integral. Specifically, we're going to go through sections 5.2 a little bit, which we did last time, and 5.3. 5.3 is the emphasis here today, which is the fundamental theorem of calculus. Really, there's two of them. Oh, 5.2, remember, was just the definite integral. I don't want to burn too much time, but I'll remind you, section 5.2, here we learned what the definite integral is. This is this symbol, right? So this big, long, curly S is called the integral symbol. And you have an A downstairs and a B upstairs. These are just numbers. And then inside here, you have a function and then the dx at the end. The dx sort of tells you what you should think of as the variable. This measures this is the signed area bounded by f of x, and the x-axis from x equals a to x equals b. And last time we spent pretty much the whole class just going over properties, like, you know, the integral from a to b of f of x is the negative of the integral from b to a of f of x. In other words, if you flip these bounds, the thing spits out a negative, or constants pop out, or you can split it up over addition and subtraction, all of those things. Today, we're going to learn the actual calculus operation. God damn it. Go, 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 go. The actual calculus operation that corresponds. And of course, that's anti-differentiation. You can probably smell that coming because the last few things we did before we started talking about areas were antiderivatives. So without further ado, the two fundamental theorems of calculus are two parts. Part one says if little f is continuous, and we define a new function, call it g, to be the integral from any constant a up to x of little f of t dt. So g of x is the area under f from a up to some point x, which is allowed to move around. Then g is differentiable. And g primed is little f of x. We've actually seen this. I gave you these theorems last Friday in brief, and we looked at a few examples where we used this. I'll show you a few more examples today. But the real gem here is part two. part 2 of the fundamental theorem of calculus is the one that we use most of the time. Specifically, like the first third of Calc 2 is all about using this. And this just says if big F is any antiderivative for little f, then the integral from a to b of little f dx is equal to capital F of b minus capital F of a. And in practice, we often write this, at least at first, as capital F with a vertical bar here like this, which just means take this function and evaluate it at these numbers, meaning plug these numbers in and then subtract. Or you'll see me use this notation sometimes with a bracket, both of which are just short for f of b minus f of a. Right, but that's it. That's it. Really, like FTC 1 and 2 are these statements, just from here to here. So we can get a little bit more practice with FTC 1. Mostly today, though, I want to get us practice with FTC 2. I'm going to show you how the chain rule interacts with FTC 1. First, though, maybe to help you sort of understand what these things are doing, I want to prove part 1 assuming part 2. So first, how are these related to each other? If part 2 is true, we can prove part 1 as a consequence. It's harder, but you can also use part 1 to prove part 2. The proof of either of these independently of each other is a little bit tricky, and it's not a proof that would be appropriate for this level. But we've seen examples, right, where we looked at like little f of t just being t, and we computed this integral just by thinking about areas, and we saw that it was t squared over 2, and we took the derivative, and yeah, the theorem worked. So I'll give you a second to write. Are there any questions about what's written here or what these things are actually, like, explicitly what they're saying? A kind of simple way to think about part 1 is that the derivative and the integral undo each other. If you differentiate through this integral, you just get the inside function with the variable swapped for the variable bound. Let's see why part 1 is true in view of part 2. So this will be a proof that part 2 implies part 1. Let capital F be an antiderivative for little f, meaning if you differentiate big F primed is little f. Then by part 2, if g of x is the integral from a to x of little f of t dt, then this would be the same as capital F of x minus capital F of a. Right? That's what part 2 says. Part 2 says that the integral of little f from a to b is f of b minus f of a. So here we're just using x in place of little b. Now if we differentiate, that would be the same as differentiating this. But when you differentiate capital F, you get, okay, that's capital F primed of x minus the derivative of capital F of a is 0 because a is a constant, so capital F of a is a constant. And then what is capital F primed? Well, capital F is an antiderivative for little f, so this is little f of x. And that's it. So if you assume that part 2 is true, if you assume that this integral is capital F of x minus capital F of a, then the derivative is little f. Okay. So down here, this is the statement of part 1, and this is the statement of part 2. So part 2 implies part 1. This interacts with the chain rule in a neat way. So this would be the conclusion of the proof. How does part 1 interact with the chain rule? Suppose g of x is defined to be the integral from some constant up to some other function. Maybe I'll call it h of x. So maybe this is x squared or e to the x or 2x minus 5x or something like that of little f of t dt. By part 2 of the fundamental theorem of calculus, this is equal to capital F of h of x minus capital F of a, where capital F is an antiderivative for little f. And now if you differentiate on both sides, g primed would be d dx of capital F of h of x minus capital F of a. And this is capital F primed of h of x times h primed of x by the chain rule, minus 0, which is capital F primed of h of x times h primed. So I'd like to work one or two more examples using part 1 of the fundamental theorem, just to give you a feel, because they do make interesting test questions and there are things that you'll see in your homework. But then the rest of the class I'm going to spend using FTC2 to evaluate integrals. That's really the gem here. Okay, but before we get to that, let's look at some examples. Do you want to see the proof at the top of the page, Daniel, or do you want to see the statement of the theorem for part 1? Okay, yeah, we'll go back here. So here's the statement of the theorem, part 1 and part 2. So some examples. I'll grab these from your book. No harm in that. Well, no, we'll just fill. Let g of x be the integral from -2 to x of sine t minus t squared dt. Can we find g primed? Okay, we want to see the bottom of the second page again there for a second. Here we go. I'll just zoom out. So if anybody's looking for anything else here, they can see it as well. And I'll definitely do some examples here with the chain rule so you can see them. But the basic idea of part 1 says if you want to differentiate something like this, just take this variable and plug it in here. And then if the thing up here isn't just your variable, then you first take this thing and plug it in here. And then you multiply by the derivative. So I'm sorry, I should finish this here to make this easier to understand. This is little f of h of x times h primed. Yeah, I encourage everybody, go ahead and add this last line here, because it helps us see what we're doing. You take the function up here, plug it into this guy, and then you multiply by the derivative of this function. Here, capital F primed is little f because capital F is an antiderivative for little f. I'll stay here for just a couple seconds more. Okay. So the problem we want to look at for our first example is a part 1 problem. We're going to use part 1 of the fundamental theorem of calculus. What's the function little f? This is little f of t. So according to the fundamental theorem, part 1, according to FTC part 1, g primed of x should just be f of x, which is the sine of x minus x squared. Why is having such a hard time focusing? That's it. That's the whole problem. You're done. We could try something else. Maybe let g of x be the integral from x to 3 of e to the negative sine t dt. Here, I don't need the chain rule yet. This isn't quite that complicated, but I do need to do something else because the variable is in the wrong position for me to use FTC1. FTC1 says if you have the integral from some constant up to your variable and you want to differentiate that thing, you can just plug that variable in here. Well, now the x is on the bottom and the 3 is on the top. So is there anything I can do to make this look more like the thing from FTC1?
You can flip the integral and make it negative.
Good, very good. So again, we want to find g primed. And here I would start by saying g of x is equal to negative integral 3 to x e to the negative sine t dt. So I can flip these bounds over from x to 3, becoming from 3 to x, as long as I pop out this negative. That was one of our properties of the definite integral from last time. And now this is something that I can apply FTC1 to. Now, by FTC part 1, g primed of x, this negative will come along for the ride, and we'll have just this guy with this variable swapped in. So that's e to the negative sine of x, or just negative e to the negative sine x. Easy peasy lemon squeezy, right? FTC1, you just plop the variable from the upper limit into the function inside the integral. That's your derivative. Let's do one with the chain rule. Let's have g of x be the integral from 0 to sine of x. And then inside here, what do we want? Let's do the natural log of t plus 1 dt. And again, I want to find g prime. This time, the bounds are in the right order. I've got constant stuff at the bottom and variable stuff at the top. So by FTC1, I should just be able to plug this in here. But I also need to multiply by the derivative of my inner function, which is this sine function. So by FTC1 and the chain rule, g primed would be, I take this and I plug it in here. So this is the natural log of sine x plus 1. And then I multiply by the derivative of this function. The derivative of sine x is cos x. Okay, so this is how we use FTC1. I could ask you for an equation of a tangent line to g, because for that you just need to find g prime and then plug in some number for x. Could ask for all sorts of fun things. But the required mechanic is that you're able to find g prime, where g is defined as an integral of some other function. So when you want to differentiate through a function that's defined as an integral, you just stop writing the integral and you plug this upper bound in for your variable here. And then if this upper bound is anything more complicated than just x itself, you use the chain rule. You multiply by the derivative. Maybe one more quick example. We could do the integral from 1 to e to the x of cos t dt, find g prime. So here g primed, I take this upper variable thingy and I plug it in for the variable here. So that would be cosine of e to the x. But then by the chain rule, I need to multiply by the derivative of this inner function. The derivative of e to the x is e to the x. All right, I think that's enough FTC1. FTC1 useful sometimes, but nowhere near as useful as FTC2. So I'll give a second if you're writing. Now let's talk about FTC part 2. What does FTC 2 really say? It says to find the integral from a to b of some function, first you find an antiderivative of little f. Then you plug in a and b and subtract. So in other words, finding the area under a curve can be done by calculating an antiderivative for that function and then plugging in the endpoints. This is a big, big deal. And this actually generalizes to a much bigger theorem called Stokes' theorem, which you'll meet at the end of Calc 3, and has lots of fascinating consequences and corollaries in physics. Maxwell's equations, for example, can be taken as a consequence of Stokes' theorem. So let's give it a shot. Let's calculate the integral from 0 to pi of cos x dx. On the one hand, we know this represents an area. Right, it's the area under cosine. Here's 0 to pi over 2. Pi is right here. And looking at the picture, it looks like there might be as much area up there as there is down here, right? Up here as there is down here. From the picture, using symmetry, it looks like this might be 0. But if I want to use the fundamental theorem, first I need to find an antiderivative and then plug in these bounds and subtract them. So an antiderivative for cosine, who differentiates to cosine? Remember, it doesn't have to be the most general antiderivative, just any antiderivative. An antiderivative for cosine is sine. So I would write this as sine x evaluated from 0 to pi, like that. So that's the antiderivative step done. And now I need to evaluate. Well, that's going to be the sine of pi minus the sine of 0. Sine of pi is 0, and sine of 0 is 0, so this is indeed 0. So we can deduce that there is indeed the same amount of area up here as there is down here in the cosine function. Fun stuff. I could calculate the integral from -3 to 3 of 1/2 x squared dx. Let's just do x squared. Forget the 1/2. There's a picture here as well. although we don't need it to do the calculation, you know what x squared looks like. And we want to integrate from -3 to +3. So we're finding this area, which certainly isn't going to be 0. I first need to find an antiderivative for x squared. Well, who differentiates to x squared? That's x cubed over 3, right? You add 1 to the power and divide by the new power. Remember all those antiderivative rules? And then I evaluate this between bounds, -3 and 3. Now, a cool fact is that this constant down here can actually pop out. This is the same as 1/3 times x cubed, evaluated from -3 to 3. So that's 1/3 times 3 cubed minus -3 cubed. We always plug in the upper minus the lower. Now 3 cubed is 27, so this is 1/3 times 27 minus -3 cubed is -3 times -3 times -3. That's -27. So this is 27 plus 27, which is 54. And 54 is divisible by 3. What is that? 12? Is that right? 54 is 9 times 6. If you divide by 3, that's 3 times 6 is, oh no, 18, right? Okay, fun question now. Since the total area is 18, what might be the area from 0 to 3? What if we didn't go from -3 to 3? We just went from 0 to 3. Yeah. By symmetry, it must be 9. And this is hinting at a theorem that I will show you after we do 1 or 2 more examples. Let me grab some examples from your textbook before we hit that theorem. So we are here in 5.3. Resonant functions, secant. Oh no, just calculating derivatives. There's your fundamental theorem. So these are all find the derivative using the fundamental theorem. That's the stuff that we were doing at the start. And now these are the sort of problems we're looking at right now. I think it would be wise for us to play around with maybe something like 27 or 28, and then something like 35, 36. Let's look at 27. So there, where were they going from 0 to 1? So here the variable is different. We're using the variable u instead of the variable x, but everything else is still the same. And it's just a change of labels, right? There's nothing Nothing about the label x that makes it special. We could use the label u or v or t or whatever we wanted. If I want to evaluate this integral, I need to find an antiderivative. How can I find an antiderivative for u plus 2 times u minus 1? Who can help me out with that? Think back to your 4.9 homework.
Something with factoring?
Not so much.
Can you simplify it?
Yeah, so it's kind of already factored, right? What do we mean when we simplify? Or what are you thinking of when you say something with factoring?
Put it back to its original form?
Yeah, let's multiply it back out. So this is the same as the integral from 0 to 1 of, if I FOIL this out, that's u squared plus 2u minus 2. So that's u squared plus u minus 2 du. And this business of putting the whole integrand, the thing inside the integral, in parentheses is an important thing. Please don't skip doing that. These parentheses matter. Now it's easy to see an antiderivative, right? Because I know how to do each one of these pieces. So an antiderivative for u squared is u cubed over 3 plus an antiderivative for u is u squared over 2 minus an antiderivative for 2 is 2u. And again, we don't need the plus c here because we're not looking for the most general antiderivative. We're just looking for any antiderivative. And then I have to evaluate this between bounds. If I plug in 1, I'll have 1 cubed over 3 plus 1 squared over 2 minus 2 times 1. And I need to subtract from that what I get when I plug in 0, always upper minus lower. Well, that's 0 cubed over 3 plus 0 squared over 2 minus 2 times 0. So all this stuff is 0. So everything's going to come from here. 1 cubed is 1, so that's 1/3. Plus 1 squared over 2, well, 1 squared is also 1, so that's 1/2 minus 2. So if I put 1/3 and 1/2 together, 1/3, my common denominator there would be 6. That's 2/6 plus 3/6, and then 2 as a ratio over 6 is 12/6. 2 plus 3 is 5. 5 minus 12 is -7. So this is -7 over 6. I'd like to ask another kind of concept question here. Since this integral came out negative, between 0 and 1, does this function spend more time above the x-axis or below the x-axis? Yeah, it spends more time below, right? Maybe some of the area that's being measured here is being measured as positive because it's above, and some is below, so it's being measured as negative. And since the total answer here is negative, that means there's got to be more area beneath the horizontal axis than above. So this function, on average, spends more time below than above, at least between 0 and 1. Questions on this example? We'll look at one more like this, and then we're going to talk a little bit about some things that are worth remembering. Let's look at the integral from 2 to 4 of v cubed minus 2v squared plus 3v minus 1 all over v squared dv. I have a similar problem at the start here as to what I had here. Namely, I don't know how to find an antiderivative for this in the form it was given. You can't just anti-differentiate the top and anti-differentiate the bottom separately. We saw that back in section 4.9 for the same reason that regular derivatives don't work that way. You've got a quotient rule, right? And there's no nice like backwards quotient rule. So what you want to do with this, just like we did here, is simplify it into some power functions. We know how to handle those. So if I can make my integral down there at the bottom with the v's kind of into something like this, then I'm in good shape. So my very first step here should be simplifying the inside. And the take-home lesson is always do as much algebraic simplification as possible before trying to do the calculus. This is v cubed over v squared minus 2v squared over v squared plus 3v over v squared minus 1 over v squared dv. And now each of those I can simplify. V cubed over v squared. So my integral is still here, integral 2 to 4. V cubed over v squared is just v. Minus 2v squared over v squared is just 2. The v squareds cancel perfectly. Plus 3v over v squared is plus 3 times 1 over v. And then minus 1 over v squared, that's v to the negative 2. So who can help me with an antiderivative? This piece, and this piece are all straight power rule things. This piece requires something special. An antiderivative for v is v squared over 2. Minus an antiderivative for 2 is 2v. Plus 3 times, what is an antiderivative for 1 over v? This one is special.
ln absolute value of v.
Good. Natural log absolute value of v. Remember, the negative first power is a special case in the power rule. And then an antiderivative for v to the negative 2?
Plus 1 over v.
Yeah, this would be minus v to the negative 1 over negative 1, right? That is a straight power rule thing. So this needs to be evaluated from 2 to 4. This minus and this minus will come together to make a plus. So this could be written as plus 1 over v also. Let's go ahead and do the evaluation. When I plug in 4, I have 4 squared over 2 minus 2 times 4. I should put this in parens, really, if I'm being careful. Plus 3 times the natural log of the absolute value of 4. And then this is plus 1 over 4, v to the negative 1, and the minus minus makes a plus. And then I subtract what I get when I plug in 2. That's 2 squared over 2 minus 2 times 2 plus 3 times the natural log of the absolute value of 2 plus 1 over 2. Four squared is 16. 16 over 2 is 8. minus 2 times 4 is also 8, plus 3 times the natural log of 4. Well, 4 is positive, so I can lose the absolute values and at least just write this as 3 ln 4, like normal, plus 1/4 minus 2 squared is 4. 4 divided by 2 is 2. Minus 2 times 2 is 4. Plus here, this is 3 times the natural log of 2. We can lose the absolute values because 2 is positive. Plus 1/2. And then we'll clean up what we can clean up. These two add up to 0. These two add up to -2. And then I'll have to distribute that negative that's out front here. So I'll get the 3 ln 4 plus 1/4. Then minus -2 is plus 2 minus 3 natural log of 2 minus 1/2. There's more that can be done here. The 2 I'll put out front. He's gonna, well, yeah, I'll put the 2 out front. That's this 2. Positive 1/4 minus 1/2 is -1/4. And then I've got 3 natural log 4 minus 3 natural log 2. Two minus 1/4 is 1 3/4, or you can think of it like 2 is 8/4. 8/4 minus 1/4 is 7/4. And then here, this is 3 times, I can factor out the 3, ln 4 minus ln 2. And using our rules for logarithms, ln 4 minus ln 2 is the ln of 4/2, which is 2. The rule I'm using in this last bit is that the ln of b minus the ln of a is the ln of b/a. And that's it, we're done. We could have stopped a ways back, but if you want a nice looking answer, right, you should combine the things that you can combine. It wouldn't have been wrong to stop here, it's just lazy. On a test, for the record, I would give you credit for this. No points lost. I do want to go back and just comment again that both of these problems, the main thing was to simplify using algebra inside the integral before trying to find an antiderivative. There's no way I could find an antiderivative for this without first writing it like this. There's no way I could find an antiderivative for this without first writing it like this. We know how to find antiderivatives for power functions, exponential functions, and some trig functions. So the only way you can do these problems is by first writing the inside as a combination of power functions, exponentials, and trig functions. Integrals don't play nice with multiplication. I can't just integrate these two pieces and then multiply them. They don't play nice with division. I can't just integrate the top and integrate the bottom and divide them. That shit doesn't work. Just like it doesn't work for regular derivatives, it doesn't work for antiderivatives. So the only way to do these is to simplify algebra-wise inside, then find your antiderivative. Simplify algebra-wise inside, then find your antiderivative. Okay, I'm going to move back to that second page now. And I want to look at the thing we observed with that parabola example, symmetries and integrals. Suppose f of x is an even function. And that we want to compute the integral from negative a to a of f of x dx, where a is some number. Well, since f of x is an even function, its graph has some symmetry. Right? Because f is even, this is equivalent to saying the graph is symmetric about the y-axis. So what can you tell me about this area as it relates to this area? What can you tell me about the relationship between A1 and A2? Yeah, they've got to be the same. So there's a few ways to think of this. The way your book says it, and probably the best way to think of this, is that the integral from negative a to a of f of x dx is the same as double the integral from 0 to a of f of x dx. And this is only if f is an even function. So this is a neat fact. If f is even, and you want to integrate from negative a to a, like negative 5 to 5 or negative 3 to 3, then you could just do the integral from 0 to 5 or from 0 to 3 and double it. For example, if I want to integrate from negative pi over 2 to pi over 2, the function cosine theta d theta, so here the variable would be theta rather than x, but it's the same thing. This would be equal to double the integral from 0 to pi over 2 cos theta d theta, because cosine is even. So if you're integrating an even function over a region that is symmetric about 0, then you could just integrate from 0 up to that upper bound and double the result, because the total area is just double the area on the right. One of the reasons this is nice is because at the end, remember, you got to plug in bounds And it's easier to plug in 0 than it is to plug in negative pi over 2. Just as a rule, 0 is usually a nice thing to plug in. Let's go ahead and do the integral. This would be 2 times, what's my antiderivative for cos theta? What is n antiderivative for cos theta?
Fine.
Yeah, sine theta. And I can evaluate this from 0 to pi over 2. So that's 2 times the sine of pi over 2 minus the sine of 0. And the sine of pi over 2 is 1. So this is 2 times 1 minus the sine of 0 is 0. So this is 2 times 1 minus 0, or just 2. And if we'd done the integral from negative pi over 2 to pi over 2, you wouldn't have this 2 here, and you would have the sine of negative pi over 2 there. The sine of negative pi over 2, if you don't remember, is negative 1. So this would be 1 minus negative 1 would still give you 2. So it's just a way of making life a little easier. And if you think that's nice, you're really going to love the next one, which has to do with odd functions. Before that, any questions on what we did here? Okay. So let's play the same sort of game. Suppose f is an odd function and we want to compute the integral from negative a to a of f of x dx. There's a picture here. Odd functions, remember, have symmetry about the origin. So here's a graph of an odd function. And maybe I want to integrate from negative a up to positive a. What do you notice about these areas?
They cancel it to 0.
Yeah, they're both the same size. So again, by symmetry, A1 is the same size as A2, but now 1 is below the x-axis and the other is above. So they cancel exactly. The integral from negative a to a of f of x dx is 0 if f of x is an odd function. A few years ago, I put a problem on my exam 1 in Calc 2 that gave students the opportunity to use this. I'll show you what that problem was in a second. But that's the main idea. Since these graphs have origin symmetry, the areas are going to be the same size. But because it's origin symmetry, not y-axis symmetry, one will be below and the other will be above. It could be the opposite of this, but always one above, one below, same size, so they add up to 0. The example here that I used on my Calc 2 test a couple years ago now, I asked students to evaluate the integral from -1 to 1 of the inverse tangent of x. You guys know how I love arctan. We don't know an antiderivative for arctan yet. We know its forward derivative is 1 over 1 plus x squared, but we don't know an antiderivative for this. But we do know that arctan is an odd function. So this integral has to be 0 because we're going from negative some number to the positive of that number. So this integral is just 0. And that's it. And the same would be true for any odd function. Very slick. I don't want to give you guys too much in any one moment. I feel like we're getting pretty close to about what I can expect you to take away from this and actually remember things. So let me just look at one or two more examples here where we're going to do a computation. It won't be anything horrible, but how about 37 is fun. Okay, so this will be our last example today. Let's integrate from 0 to 1 the function x to the e plus e to the x dx. Neither of these are even nor odd, so I can't use any of my symmetry exploits. So it's just a matter of finding an antiderivative. Can anybody help me find an antiderivative for x to the e?
Wouldn't it just be x to the e?
So e to the x is its own derivative and antiderivative, but x to the e is a different kind of function. It's not an exponential. Remember, e is a constant, right? This is like x to the 2.7. So this first piece has its antiderivative coming from the power rule. But the second piece, e to the x, he is his own derivative and antiderivative. So he stays the same. And now if I plug in my upper bound, I'll have 1 to the e plus 1 over e plus 1 plus e to the 1 minus, I plug in my lower bound, I'll have 0 to the e plus 1 over e plus 1 plus e to the 0. if you take the number 1 and raise it to any power, you're just going to get 1. So 1 to the e plus first power is just 1. So this first piece is 1 over e plus 1. And e to the 1 is e. The 0 raised to any constant power is just 0. So this is 0 over e plus 1, or 0 plus e to the 0, which is 1. So here we get 1 over e plus 1 plus e minus 1. That's it. So you got to remember your antiderivative rules. There's no escaping that stuff, that 4.9 stuff that we did before we started talking about Riemann sums. Hugely important here. And if you can tell by the kind of balance of example today is how many part 1 problems there are versus part 2 problems. Part 2 is way more important. They're cutesy kind of fun, like take the derivative of this function problems that you can answer with fundamental theorem part 1. But it's part 2 of FTC that we use all the fucking time. Not just here, but also all through Calc 2, you're going to use it. It's definitely the more important guy. So this process of finding an antiderivative is a big deal. And sometimes it's very hard. No person can find an antiderivative for every function. For example, e to the x over x, ln x over x. Wait, no, this one I gotta take back. This one's not hard. 1 over ln x sine x over x e to the x squared. These all have no, we'll call it nice antiderivative. Meaning to write down an antiderivative for any of these requires some sort of infinite process, which means integral 0 to 1 of e to the x over x dx, integral from, let's say, 5 to 7 of 1 over ln x dx, or the integral from 0 to 10 of sine x over x dx, or the integral from -1 to 1 of e to the negative x squared dx. These are all incredibly hard. To find. Basically, computing these areas, computing these definite integrals, comes down to finding an antiderivative. If you can't find an antiderivative, you're going to have a very tough time finding the exact area. You can use Riemann sums to approximate the area, and that's great. But where we're going from here is wanting to find exact areas, and that is quite tricky. And when I say, you know, this is hard, I don't just mean like you can't do it. I mean like I can't do it, like no one can do it. There's a theorem that's been proven that all of these are functions that don't have any closed form antiderivative. Closed form means like not an infinite expression. When you get towards the end of Calc 1, I'll show you how to find antiderivatives for this, this, and this. But they're not going to be nice. They're going to be quite complicated looking. And this guy is even more elusive. You find an antiderivative for this, I know a handful of analytic number theorists that would love to hear from. All right, that's where I'm going to leave it for today. You guys, I will be popping open a fresh homework for you to look at in a little bit. I know we're a smidgen early, but I don't think anybody will complain about that. Most of this week's homework will be coming from 5.2, 5.3. Oh no, you already have your homework for this week. Yeah, you don't need to stress. And then next week, we will start playing around with the substitution rule, which is that thing that I warned you guys about. I'll give you a little introduction to the substitution rule on Friday. And then I will teach you guys how to do this properly next week. Now, next week is also Thanksgiving, which means that we will not have a meeting on Friday because Thursday is Thanksgiving, so no meeting on Friday, but we will have a meeting on Wednesday and we will have a meeting on Monday. Also, the last day of class is December 4th. So this is going to be the day of exam 3. Exam 3 will take place in class, like during class time, just like our other midterms, on December 4th. And then your final exam is also coming up. I would like you guys to mark this in your phone right now, put an alarm in, do whatever you got to do to make sure that you do not forget. This is your section, right? Yeah. That your final exam is December 7th at 1 p.m. That's not our normal time. And December 7th is the Monday after class ends. So please put an event in your calendar right now. Set several alarms to remind yourself. This is where we'll be going. Any questions for me before I let you guys go? All right, the grade book should be all up.
No, thank you.
I went through and marked everything, whether you handed it in late or took the test at a strange time or emailed me parts of it. All the study guide grades and exam grades should be in the grade book. So please take a second to look at that. If there's anything that doesn't look right to you, let me know so we can talk about it and figure it out. Andrew says the last recording doesn't work on YouTube. I just uploaded that a minute ago, so maybe give it a second to finish processing, Andrew, but if it's still not working, let me know. Let's see. So 2311. Is it working for me? It's working now. Yeah, so this should be okay. The lecture from last time should be up and running now, but if it's still not working, let me know. Okay, if there's anything else you guys need to talk to me about, you can always come by office hours or send me an email. Otherwise, I will see you next time. Take care.